So welcome back. So let's have a look. Got to get back on. Yes. So we got to this stage, speeding up and slowing down. So if I am on a number line, and here's my 0. If I'm hanging out down here, positive addresses or negative addresses? Negative addresses. Left is negative, right is positive, up is positive, down is negative, unless there's a good reason not to be. Yeah. So negative addresses, positive addresses. If I'm here and I go like that, positive velocity or negative velocity? Because I'm going in a positive direction. So if my v is like that, supposing I'm here and I go like that with my v, positive velocity? So the velocity doesn't depend upon, the sign of the velocity doesn't depend upon where I am. I can be in a negative part of the line and still have a positive velocity, or a positive part of the line and still have a positive velocity. Yeah? Want to know the direction of travel? Look at the velocity. Yeah. If I have a negative acceleration, am I speeding up, am I slowing down, or what? So depends on the velocity. Agreed? Not negative acceleration means slowing down. I mean, negative velocity meant going in a specific direction. But now acceleration, what's the point in the sign if it doesn't tell you anything? It turns out that you're perfectly right. It's perfectly right. It's a real, well, it depends. And I want to kind of show you that. So if we have our velocity versus our time, and let's say that our acceleration equals plus 2 meters per second every second. Now that's the way I was taught it, meters per second every second. So you change your velocity by plus 2 every second. That's what that literally means. Let's say it's time t equals 0 and I'm at, say, minus 10 meters per second. So at 1 second I add 2 on, minus 8. At 2 seconds, minus 6. At 3 seconds, minus 4. At 4 seconds, minus 2. At 5 seconds, 0. So what's happened here, what's happened here is I'm traveling in a negative direction, but I'm going slower and slower and slower. So I'm traveling in a negative direction, but I'm going slower and slower and slower. So my velocity is negative, but my acceleration is positive. And I'm slowing down. And then I stopped. So what happens at 6 seconds? Well, plus 2, because every time we add on plus 2. 7 seconds plus 4. 8 seconds plus 6. 9 seconds plus 8. 10 seconds plus 10. Oh, I stopped. And now I went back like that. And here I had a positive velocity. And the acceleration was like, yeah, and a positive acceleration. So I slow down when my acceleration is in the positive direction and my velocity is in the negative direction. And I speed up when my velocity is in the positive direction and my acceleration is in the positive direction. Yep.
Now I understand how you're going in a negative direction. You start from -10 and you go to 0.
My speed, my velocity goes from -10. This is velocity. So I said, I am going in a negative direction.
But that's where you start on negative side.
Yeah, I start, I'm anywhere. I don't tell you where I am on the number line. I'm somewhere. I never tell you where I am on the number line. All you know is at the beginning, when the clock says 0, I'm travelling in that direction at 10 meters per second, yeah? And then I'm going a bit slower, and then I'm going a bit slower, and then a bit slower, and then a bit slower. And then at some point I stop. Now in that part of the journey, my velocity is negative, but my acceleration is positive. So I'm going, and I'm getting slower and slower and slower and slower. And now what happens is, I still got an acceleration, so now I'm going faster and faster and faster and faster and faster. It's a bit like this. It's like, take this. Which way is the acceleration going to be? Right, throw it up in the air. Which direction is the acceleration going to be? Oh, acceleration is caused by the force. So the force is going to be downwards. So the acceleration is going to be downwards. So acceleration is going to be downwards. Forget about my hand. Okay, I wasn't clear. Forget about my hand. Once it leaves my hand, acceleration is downwards, velocity is upwards. What happens? It slows down, it stops, then it speeds up again. So it's the same pattern. So whenever the acceleration is in the same direction, lost my pen. Whenever the acceleration is in the same direction, as the velocity speed up, no matter what it is. So, if the acceleration is positive and the velocity is positive, you're speeding up while going in a positive direction. When the acceleration is negative and the velocity is negative, you're speeding up while going in a negative direction. When the acceleration is negative and the velocity is positive, you're slowing down while going in a positive direction. And when the velocity is negative and the acceleration is positive, you're slowing down while going in a negative direction. The velocity always gives you the direction, but you can't just look at the acceleration and get whether you're speeding up and slowing down. And that's the most common mistake. So at t equals 5 seconds, an object has a velocity of that and an acceleration of that. So here's my object. It has a velocity of +2 meters per second. Has an acceleration of -8 meters per second squared. So this would be slowing down, but going in pos direction. Yeah. So that's a good thing to remember. So can you do this one for me? Let's just do it. Starts from rest. After 4 seconds, it has a velocity of -12 meters per second and an acceleration of -4. So what is it doing? Speeding up or slowing down? Speeding up. And which direction is it going in? Negative, yeah. So speeding up, going in a negative direction. B on that one. Cool. Motion graphs. These 3 graphs are not the same, and they're not even the same journey. So, tip, always get a highlighter, get something, but make sure you read what the axes are. This is the position or the coordinate versus time. This is the velocity versus time. And this is the acceleration versus time. So they're the same shape, same size, but they're not the same thing at all. They don't go together. If I have this acceleration, I don't get that velocity-time relationship, and I don't get that displacement, that position-time relationship. So they don't even go together. They're just straight line graphs. That's all I'm about, a straight line graph. because the question I want to pose to you is, so with graphs, there's always two things you ask about. One is the slope, and the other one is the area under the curve. So what do these things mean? And the way you get it is you look at the units. So the slope is always rise over run. So if this is in meters and that's in second, my slope is in meters per second. And there's an old adage that if it walks like a duck and it quacks like a duck and it swims like a duck, it's a duck. And if it's got units of meters per second, it's velocity. Okay. The area under the curve, well, that's going to be meters times seconds. And although that's a thing, we have no clear interpretation of it. It's not something where we go, aha, that means so-and-so. I have no idea what that means. It's a thing. It is calculable. It's there. Maybe it's some insight that nobody's had, or at least I've not had, but we don't have a name for it. It's just there. If I plot velocity versus time, then my slope would be meters per second, and I know that's acceleration because that's the way I was trained. Meters per second, that's acceleration. The area is meters per second times seconds, which is meters. If it walks like a duck and it quacks like a duck and it swims like a duck, that's displacement. That's the displacement that occurs during this part of the journey. That's kind of interesting. That's a very useful graph. You want to go by slope, you go the other one way. You want to do the area, you go the other way. It's a very interesting thing. For this third one, the slope is meters per second squared per second. That's meters per second per second per second, which is acceleration per second, if you like. Unfortunately, what they'd say is it was meters per second to the fourth, I think. No, third cubed. Meters per second cubed. Acceleration per second is change of acceleration per second. And I say here no clear meaning. And that's because I had my physics hat on and wasn't really thinking about it. What do engineers call change of acceleration with time? Anybody know? Pardon? Oh, what? I think he's calling me names. What? It's jerk. It's J-E-R-K, I guess. And what's going on? You're pushing. So to jerk is not the same as to push, okay? It's a colloquial expression, so let's be a bit clear about it. This is pushing, you know? Jerking is like that, yeah? That's a jerk. I pull it like that, yeah? It's not a pull, it's a rapid change of force, agreed? It's very useful at times. You want to get this wrench to turn, you jerk on it. You don't pull, you jerk on it. And it has a different effect because you change the rate, change the force quickly in time. That's very interesting. And that's, physicists don't care about it because we don't look at real situations very often. Or maybe just my failing, I don't know, maybe it was one of those things I was sleeping through in class, but engineers really care about that. So jerk is really useful. The area under the curve is meters per second times seconds, which is meters per second, which would be like the average velocity for that bed. So it's very fascinating what you can do with these things. We're going to spend a bit of time today and then a bit of time next time looking at how things change, how we can represent things graphically. So truthfully, it's very hard for me to make a machine that would be able to change its position versus time at a sharp point like that, when this is in seconds. But I could do it like on an interstate if I had hours on the time rather than seconds. So you've got to forgive these graphs because they come to right sharp points, and in reality we can't make machines very easily that can do that. It has to be a very light machine to be able to make those changes as quick. But I don't want to draw a realistic diagram with all the curves, and it just gets complicated. So we're just going to imagine straight lines. And notice they are three different types of graph: position, velocity, acceleration. Different. Let's try and interpret them. What can you tell me about the velocity of this object? So remember, this is a straight line. We're only going on a straight line. We've just got an object. What can you tell me about the velocity of this object over the first second? It's a constant velocity, isn't it? Yeah? Because it's steadily changing its position in time. It goes by plus 10 meters in the first half second and another 10 meters in the second half second. So constant velocity, constant positive velocity, and I can even tell you that it's plus 20 meters per second. Yeah? What can you tell me about the velocity of the object in the second? It's zero, isn't it? No change of position in time. What can you tell me about the velocity of the object in the third second? It's going to be a constant velocity. It is 10 meters per second, and it's positive. Yeah? What can you tell me about the velocity in the third to fourth seconds, 3 to 4 seconds? It's constant, it's negative, and it's minus 30 meters per second. Yes? And so on. When is the first time that this object changes direction? At what time does this object change direction? Is it 3 or is it 4? Let's have a vote on that. A is 3, B is 4. At what instant does it change direction? A is 3, B is 4. A is 3, B is 4. E is, I don't care, but A is 3, B is 4. What do you think? A is 3, B is 4. I've got a few people, I think, thinking about it. A is 3, B is 4. I give it just a little bit more. A is 3, B is 4. I'm right curious about what this comes out to be. A is 3, B is 4. I'll give you until the minute's up. A is 3, B is 4. A is 3, B is 4. A is 3, B is 4. Let's do that. What's it going to look like? Whoa, yeah, again, quite split. The answer is 3. Because this is a positive, where's my pen gone? Sorry. This is a positive velocity, so I'm going in a positive direction. And that's a negative velocity. I'm going in a negative direction, so I have to change direction at that point there. What's the significance of 4? 4 is when you return to your starting point. So 4 is when you return to your starting point. When do I stop for the second time? At what time do I stop for the second time? 5 seconds, because I start this horizontal bit. Yeah, so interpretable, yeah. Look at the second diagram. When do I stop for the first time? I'm going to give you a couple of points. There's A, there's B, there's C. Pick. When do you stop for the first time? A, B, or C? Wow, you guys are getting fast. I'll give you until 30 seconds. Very good. Okay, boom, good. Okay, stop. And what's it going to be? Whoa. I love it when it's kind of even. It's like, because it's a more interesting question. The answer is B. When does it stop? It stops when it's got 0 velocity. Hold on, I thought it was when it was horizontal. Yeah, in a position versus time graph, it stops when it doesn't change its position in time. But on a velocity versus time graph, it stops when it crosses the origin. So what does A mean? A means when you start going at a maximum speed in this case. This is the beginning of your 15 meter per second zooming down the road. So very different interpretation. Can you tell me what is the actual time when you stop? There's no, you're going to have to shout this out because a brave soul is going to have to shout this out because there's... So can you get me the actual precise number? It's not 0.5. I would not accept it. I know it's close, but I want exactly the number. So you got to look in detail. It's 4.6. And and this is just going to the next level. In fundamentals, 4.5 in this. So this goes 1 step down, 2 steps down, 3 steps down, 4 steps down, 5 steps down. And we are 3 of those steps, yeah? It's a straight line. So that means I divide my horizontal bit into 5 steps. And we are 3 along. Yeah, there's 5 steps vertically and we went 3 of them. That means there's 5 steps horizontally, so we must have gone 3 of them. So 4.6. It's going to be, I'm going to push you on that. 4.6. Get the exact number. I would return to my origin when that area was balanced by that area. That's a positive displacement, that's a negative displacement, and so on. I won't worry about this so much. It's got a different interpretation again. And that's what we're going to do, basically. Let's just have a quick look at this one. At what is the object's direction of motion at 6.5 seconds? So I come along here to 6.5 seconds. I have a position versus time. Oh, 5 point... Sorry? 6... Oh, thanks. Yes, I'm giving you a hard time about precision. I'm going to hold one out. Life is ironic sometimes, but yeah. And I was thinking, hold on, it's not even moving. So what is my direction of motion there? It's negative because it's a negative velocity. What is the object's average velocity between... Oh, average velocity between 1 and 4 seconds. 1 and 4 seconds. Average velocity is rise over run. So that would be plus 20, and that would be 3. So my average velocity, which equals delta x by delta t, which equals x final minus x initial over t final minus t initial, which equals 0 minus 20 over 4 minus 1, which equals 20 over 3, which equals 6.66, I think. Yep. So that's how you do that. When does the object stop for the first time? Position, so it stops at there for the first time. And what is the object's instantaneous velocity at 5.5? 5.50. What is the object's displacement? Oh, yeah, I can. What is the object's displacement between 1 and 5 seconds? Delta x between 1 and 5 seconds is equal to x final minus x initial, which equals, there's my x final, plus 30, minus, there's my x initial, minus 20, which equals plus 50 meters. And you can kind of see it, can't you? That's the displacement. You're going in a positive direction and you went by 50 meters. Can you see how? Again, this is not hard math, but it's doing the right math on the right interpretation of the words and the diagrams and the like. So this is mathematically not hard. You've been well trained mathematically for this. But what I got to get you to do now is slow down before you dive into the math and check your visualization. It's what you're applying the math to, which is the most important thing. And to some extent, I just wish I could kind of like give you all pills and just slow you down a bit for about 2 weeks, and just have you go through things a bit slower and double check and not assume so many things. We all do it, but we got to learn techniques so we kind of double check ourselves and do it less frequently. We all make slips, we all misinterpret, but you've got to do it less and less often. And for that, I think it's just slow down a little bit. Okay? So next time we'll do, we'll actually use these to actually develop some equations of motion, kinematic equations and the like. So I'll see you guys next time.